Okay, folks, I am coming at you from the very empty physics classroom, and I'm going to film for you today a lab called Rotational Inertia, which starts on page 14 in your lab packets. This lab is affectionately nicknamed as the T-bar lab, and you can see this white T-shaped PVC apparatus. It's set up on a ring stand. And I'm going to zoom in right here, but wrapped around the base of that is a string. And if you pull on that string, the tension in the string creates a torque, since that tension force is offset from the center of that by the radius of that vertical pipe. Force times radius, or moment arm, is torque. And if I back up and I pull on that, that torque causes an angular acceleration around the pipe and the T apparatus there at the top. So that is the apparatus that we're going to use today, and what we're going to do is we're going to systematically apply different torques to that system and then measure and determine the corresponding angular acceleration, and therefore hopefully determine the moment of inertia of this white T-bar apparatus. If you look at the T-bar apparatus, you can kind of see that it's made up of a lot of different parts. So if you think back to that table of common moments of inertia for common shapes, that we can sort of look at this. If we dissect it a little bit, we can see that some of what we're looking at here are this vertical piece over here, this vertical tube. Well, that's kind of like a really long ring. We also have kind of like a helicopter blade there at the top, the horizontal part of the T-bar. So that's like a horizontal rod of a certain length rotating about its center. And then on the ends of that rod, we have these point masses. So there's one on this side, and then there's one all the way there on the other side too. So we have an mr squared there and an mr squared there. If we add those pieces together, we should be able to get pretty close to the value that we determine by looking at torques and corresponding angular accelerations. So that is pretty much the idea. The only other thing I'm going to add to this overall description before we start taking some data is the way we're going to apply those torques is we are actually going to hang a weight over that pulley there. And you can see on the table I've got a bunch of weights ready to go. So as that weight drops, it's going to have a linear acceleration moving down towards the floor, which we're going to use kinematics to find. And then we can relate that linear acceleration of the weights moving towards the floor to an angular acceleration of the vertical pipe and the T-bar. So that is pretty much the idea. Set up right now just with 50 grams hanging over the pulley. You could see the string wrapped around the vertical tube. And I'm just gonna let it go. I'm not gonna record anything right now. But you would expect that if I let this go, that 50-gram mass there that's hanging on the hook should just drop straight down to the floor at the acceleration due to gravity. But you can see, I've already let go of it, that it's moving towards the floor really slowly. And the reason for that is, as you guessed, is because of all that inertia in the system that is resisting any kind of acceleration, either rotational or linear. It would be the exact same effect if instead of the T-bar apparatus, that string were dragging a heavy object sliding across the table. So what you could see, I just hit the floor, so it's not accelerating anymore. But that linear acceleration we could determine using kinematics if we record the time, and that's going to correspond to the rotational acceleration. So if you think about independent variable, dependent variable, and we're overall trying to determine the moment of inertia of the T-bar, so really input variable is torque, so that's what we're going to be manipulating. That's our independent variable, and the angular acceleration is going to depend on that, so that's our dependent variable. And the constant that we're hoping stays the same through all of those trials is the moment of inertia. So as you're moving through this, kind of think about it from that perspective. And if we break that down just a little bit more, really what we're keeping track of is the amount of mass that we put on that hook, because that's what's putting the tension into that string and creating the torque, and the time that it takes for that mass to drop. That's what's going to help us find what the linear acceleration is, and then we can calculate all the other parameters that we need. And I've got another video that's going to go through a lot of the details of the analysis. Also, those details kind of unfold as you look at page 15 in your packet. Page 15 kind of guides you through finding the torque, the angular acceleration, and the moment of inertia for one trial. And then you're going to repeat this, or I'm going to repeat this, for 4 or 5 additional masses. So really in this video, I'm going to just concentrate on how much mass I put on that pulley and how much time it takes the pulley to drop, or sorry, the mass to drop from the pulley down to the floor. Okay, one other value that we're going to need is what's the height from which it's dropping. How far does it go under its influence of gravity offset by the rotational inertia? We already measured that, and it's 75.5 centimeters from the bottom of the mass hanger to the floor. Another thing that we're going to need to know is what the radius of that vertical tube is. Not such an easy thing to do unless you have the right tool. So I'm going to use this vernier caliper to measure that full outer diameter of that tube. And when I look at the scale, that's looking like 2.66 centimeters of diameter. Okay, I'm set up here for a 50-gram trial, and I'm going to release this from rest from that 75.5 centimeter height and see how much time it takes for that mass to drop to the floor. Here we go. On your mark, get set, go. Slow and steady, but you can see that T-bar is speeding up and the mass is speeding up towards the floor. We have a linear acceleration and a rotational acceleration. So let's watch this hit the floor. Very exciting. Okay, that was 29.05 seconds. Okay, so I've added 50 grams, so we have a total of 100 grams hanging off that pulley. And here we go. 1, 2, 3, go. Hopefully we will see that this time should be a little bit shorter, as this is hopefully moving a little quicker. That was 18.83 seconds at a total of 200. On your mark, get set, go. You can see how that thing's whipping around. .09 seconds. You can see that thing's moving quite a bit quicker now. Grams hanging, and on your mark, get set, go. I'll zoom back so you can really see this is starting to go pretty quick. I would not want to get in the way of that white thing. 9.65 seconds. Okay, next trial, this should be 500 grams hanging over the pulley. On your mark, get set, go. That looks like 7.84 seconds. 600 grams. On your mark, get set, go. .9 seconds.